In this segment, we'll continue to analyze the systr.dll spyware binary. To aid in our analysis, we'll use the hexray decompiler. Hexray decompiler is a plugin module for IDA Pro 5.1 and later. It creates a C-like pseudocode representation of the disassembled functions. Hexray decompiler comes with a simple text configuration file that we can edit. It's called hexrays.cfg and placed in the IDA configuration folder. Let's open it with Notepad. Currently, there are only a handful of options to set. For example, we can change the background color of various parts of the pseudocode window, as I have done here. The function body background color is set to azure, and the variable declaration area is corn silk, a light yellow color. Let's set the block indentation to 3 spaces to make the code easier to read. Let's also set the comment indentation to 18 and reduce the right margin to 40. Our demo window has to fit on a typical 1200 by 800 laptop screen, so these adjustments are quite useful. As the decompiler evolves, there will be more options that the user can change. Let's save the file and get back to our analysis. To launch the hexray decompiler, we can either use the View, Open Subviews, pseudocode menu, or we can simply press the F5 hotkey assigned to the plugin. We position our cursor within the function we wish to decompile and press F5. We could also press Tab. Please note that hexrays cannot decompile code that lies outside the functions. That's why it's crucial to refine the disassembly as much as possible before trying to decompile. As you see, we got another tab added to our window list. It's called pseudocode-A. As we decompile more functions, hexrays will add more windows to the list. If we were to position our cursor outside the function and then try to decompile, we would get an error message. Let's try it. Yes, hexrays complains. Let's get back to our function. Hexrays was able to transfer the argument names to the pseudocode, and it looks very much like a function written in the C language. Also note that the code area has a light blue background color, just as we specified in the configuration file. Hexrays was able to transfer the argument names to the pseudocode, and it looks very much like a function written in the C language. Also note that the code area has a light blue background color, just as we specified in the configuration file. Now, let's read the code and see if we can improve the representation. Hexrays has already transferred the parameters for the function. We see that the second parameter, fdword reason, is compared to 1. Let's change this magic value to a symbolic constant. If you have done any Windows DLL programming, you may remember that the DLL initialization is called with DLL process attach, DLL thread attach, as well as the detach counterparts for the same. We will right-click on the magic value 1 and pick enum, or we could just press M to find the corresponding symbolic constant for our magic value. Pick New to search for it in the standard symbolic constants list. We know that the constant should start with DLL, so we key in those 3 letters to home in on the choices in the long list. If we scroll down the list a little, we can see the DLL process attached is the one that we want. Now it looks much better. When a process first loads the DLL, it sets up the file handles. This looks like typical runtime library initialization code. Let's explore this code with hexrays. We can double-click on a function name in the pseudocode window to decompile it. For example, If we double-click on OS Setup File Handles, hexray takes us to that function and decompiles it. To synchronize the disassembly with the pseudocode window, we press Tab. Now we have them side by side. Pressing Escape takes us back to where we were in the pseudocode. Escape and then Tab. We'll focus on the libmain since the other functions in the routine are from the runtime library. As you can see in the disassembly, the libmain is called indirectly via a register value, EAX, which is loaded from memory. That's most likely a pointer to the actual function body. If we double-click on libmain, we go to the line that has the libmain offset value. It is initialized with the offset of the actual libmain function. Let's follow that offset to locate the function body. Yes, this is the libmain we wanted to look at. Now, let's press F5 to decompile it. We've got another pseudocode window added to our list. If we double-click the function name in the pseudocode window, hexray locates that function and shows us the code in the same pseudocode window. If we hit F5 or Tab while we are in the disassembly, then we get a new pseudocode window, pseudocode-B. Since we are no longer interested in the DLL entry point code, we will close pseudocode-A. Let's read the code in libmain to understand it better. We know what the first argument should be, so let's give it a more descriptive name. Right-click and pick Rename LVAR or press N. Let's call it hEnst. As you can see, hexray has updated the function parameter list accordingly. We see that hEnst is saved in a global variable. We will rename the global variable toghEnst. Right-click and pick Rename Global Item or press N. Notice that hexray also rename the variable everywhere it is used within the function. The hEnst is used to initialize the window class. There is an API call, OpenMutex, at the start. It tries to open a mutex name, syshandle number 5. If it is successful, then it sets the result to 1 and returns. If it cannot open the mutex, then it tries to create it. It also initializes a window class structure and registers it. The return value from the Create Window API is saved in another global. Let's give it a better name. We'll call it gwinhandle. Let's also change the magic parameter value, 0hex 1f0001, in the OpenMutex call to something more readable. We press M for enum, search in the standard list, and we find Mutex All Access. The most important part of this function is the window proc field of the window class. This gives us the pointer for the function that will handle all messages sent to this window class. Let's rename it to window proc. We're done analyzing libmain. Now let's double-click on window proc and take a closer look at it. The parameters are already named properly. We see that the parameter message is being compared against some magic numbers. Let's try to convert them to meaningful names. We press M and search in the standard list. It should start with WM. We see that WM closed is our magic value. Let's pick that. We'll do the same for the rest of the magic constants. It appears that the window proc is doing things when the timer message comes in. It sets up a timer at different intervals. We see that the first one is for 1 millisecond. The second one is for 10 minutes. The third one is for 100 minutes. The fourth one is a larger number. Let's use the IDA calculator to find out. It is for 12 hours. But where are the timers set the first time? Let's scroll down the listing. We see that WM Create Message creates an edit window and also sets up the timers. We also notice that this function handles window size message and changes its size. Now, let's look at the timer messages in more detail. There are several functions it calls when the timer events messages are received. We'll try to figure out what each one does and rename them accordingly. Every millisecond, the first timer goes off, and it does something to the registry. It is registering some kind of handler for the desktop. It also changes the home page for the Internet Explorer. It also checks for uninstall HP key. If it is present, then it uses the Move File API. Let's convert the last parameter from the magic value 4 to something more intelligible. We press M, click on Yes, and then type in Move. Looks like Move File Delay Until Reboot is the one. The file name is set to its own path, so it will remove itself on the next reboot. It must be some kind of uninstall feature. It also deletes a key from the Task Scheduler Registry subkey. Let's call this function Manipulate Registry Keys. We'll press Escape to get back to window proc. Note that the function name in the disassembly is also updated to match Manipulate Registry Keys. As you refine the decompilation, the disassembly also improves and vice versa. Now, let's double-click on the function it calls in response to the second timer message. It shows a message box with a scary message, warning the user that the computer has spyware. MessageBox API returns an int. So let's change the type of variable result. Right-click on Result and choose Set LVAR Type. Or we could press Y. We can rename this function Show Scary Message. Let's press Escape to get back to window proc. We'll double-click on the function it calls in response to the third timer message. This one simply opens a browser window and takes the user to a site where it will run some kind of PHP script. We can replace the last parameter with a symbolic constant. Press M, pick New. It should start with SW. Pick SW Show. There's not much else in this function. Let's name it Web Browse Too Hot Offers. Let's press Escape to get back to Window Proc. We'll double-click on the function it calls in response to the fourth timer message. This one is a bit more involved. It checks to see if the computer is connected to the Internet, allocates some memory, 100,000 bytes. It then opens an Internet session. The first parameter to the Internet Get Connected state should be Connection State Flags. Let's call it inet con flags. It checks the first bit to see if it's set. This is used to test if the connection is through a modem. We'll put in a comment by pressing /. Type in, "Are we using a modem to connect?" Notice there's a problem with the parameters to the Internet Open API. This API takes only 5 parameters, but somehow hexrays is showing us 6. This happens occasionally when the type information for the function is unavailable. Let's fix it ourselves. Right-click on the API and pick Set Item Type, or press Y. The calling convention should be standard call, and the first parameter should be deleted. The return value from the Internet Open is saved in a local variable. Let's rename that inet handle. It's copied to v5. Let's call that iHandle. The second API call is opening an executable file on a website. It then reads the file into the buffer that was allocated above. It then makes up a file name in the system32 directory and creates a file called 39.exe. We can rename v1 to inet file handle. v6 is set to v1, so we name that inet f handle. Not very creative, but it's easier to follow the code this way. Let's rename v2 to new f handle. Now we know that this function retrieves an executable file from the Internet and drops it into the Windows System32 folder. Let's call it Download Trojan from Internet. Let's get back to Window Proc. The pseudocode of Window Proc has 105 lines of C code. Compare that to the 486 lines of assembler code in the disassembly. That's more than 4 times the length of the one in C. Which one would you rather have to read? While you are pondering that question, let's take a coffee break.